memoryless property means the property, okay, the probability of waiting an additional period of time is independent of the time that you have already waited. Okay, for example, if you have an electronics item and it has been working, say you have a computer and say it has been working for 1 year, okay, so its probability of failing in the next 1 hour is same if you have been if it's if the computer is either 1 year old or 5 year old or it's just brand new. Okay, it doesn't depend on its past, it doesn't hold the memory how long you have been using it. I have used my computer for either 5 years or 1 year or it's brand new, the probability of it failing in the next 1 hour remains constant. That's what memoryless property means. I hope memoryless property is clear. Let me write it down for you. Probability of waiting for an additional period of time for an event to occur, in our case failure of our computer, is independent. This is what memoryless means. Of how long you have already waited. Again, I'll write down the example. So for example, lifetime of computer parts or electronics items, okay, whatever computer we are discussing about, they don't wear and tear. So when this whole definition of exponential or memoryless property, is defined for all the objects that don't wear and tear, they fail randomly. Okay, and that's what is the case with computer parts, electronics items. So that's why we can model it as an exponential distribution. Okay, so for example, lifetime of computer parts, I'll write it down, computer parts follow exponential distribution. We can model them as exponential because they do not wear and tear. Okay, the failure, okay, where failure is due to, what is the reason for, due to a constant random rate, some random thing, due to a constant random rate of failure. There will be some constant random rate for failure. Okay, rather than degradation over time because of the wear and tear. This is the same thing I have written down for you. Okay, rather than degradation due to failure. Okay, so this is what memoryless property means. And now let's prove this mathematically also. Okay, and this memoryless property is very much important. So this is very useful in doing reliability analysis of any product, how reliable the product is. Okay, this is used for reliability analysis of electronic system because we can model the system in as exponential distribution, because the reason for failure is some constant random rate instead of wear and tear. So this is one of the use case. So I'll write it, use case is reliability analysis. This is the use case for exponential distribution reliability analysis, and this is because of this memoryless property. It doesn't remember anything. Okay, so let's do the maths. So let's come back to the CDF of PDF and CDF of exponential distribution. What is the PDF and CDF? Do you remember that? What is the PDF? PDF was lambda into e to the power minus lambda x, and CDF was 1 minus e to the power minus lambda x, where what was x? Lambda is the average. I hope we remember that average. Let me see if in my notes. Lambda is the average waiting time. Average rate, average failure rate. Okay, so we can write that average time till next failure. Okay, so this is a exponential distribution. So let's do the maths. So we have this. So how is the CDF defined? What is the CDF? Okay, let's define the CDF. So all these notes we'll just check in the Wikipedia if there is something missing here. Okay, so the CDF is defined. What does this mean? This CDF is equal to, this is the probability of x less than or equal to x. This is capital X, is small x. So this is the CDF defined as probability of all the events which is less than or equal to x. So now if I have to find, okay, if I have to find what is the probability of x greater than x, what will that be? So say we have a continuous distribution, any continuous distribution. So this is there. Say this is. So our generally the graph of exponential is something like this. This is your exponential curve. And if this is our x, okay, and if this is the region of x less than or equal to x, this whole region, if I want to find the probability of x greater than x, then what will I do? We know this is the formula. We know the area under the curve is, total area under the curve is 1. You need to find this. So total area under curve is equal to 1. So can we say this is equal to that probability of x less than or equal to x plus probability of x greater than x is equal to 1. We know this is our CDF. Then using this, can we find this? So the whole area which is less than or equal to x is this one, and the remaining, this part, can we say that x is greater than x? This part after x. So if we subtract it from 1, can we get that? So what will that be? So probability of x greater than x is equal to 1 minus probability of x less than or equal to x. This is equal to 1 minus our CDF. This is 1 minus e to the power lambda x, and this will be equal to e to the power lambda x. This 1 and 1 will get cancelled, and this minus will become plus. So now this is our probability of seeing any value greater than x. So let's define a use case for understanding the memoryless property. So our use case would be, say for example, we'll see this mathematically. Let's suppose we know that an electronic item has lasted for, say, some x greater than t. So it has lasted for some x time which is greater than t, and then we want to find the probability of that. What is the probability of it lasting for another s hours? Okay, another, so it has lasted till for t hours, and now I want to find that will it last another s hours? Okay, and then we will find that whether it's dependent on the t that it has lasted for. Say for example, t is equal to 5 years. Okay, I know that this has lasted for greater than 5 years in this moment. X is greater than t, that is it has lasted for 5 years. Now I want to find that will it last for another 1 year. So that will be my t plus s time, 5 plus 1 year. So I have to find now whether this time is dependent on the time that it has already survived. Okay, so this is what we want to find. Let me rub it off. So the question, let me write the statement. Suppose we know that an electronic item has lasted, haha, sorry, lasted for some x years or x time which is greater than t, and then what will be the probability with the probability that it will last for some more additional time, additional time, say s. What is the probability? We want to find that. So what will be the probability? So what will it be? So now we want to, what is the problem at hand? We want to find probability of x greater than t plus s, that my electronic item has survived for 5 years plus one more year. What is the probability of that, given that it has already survived, it has already survived for greater than t years, for some t time. So probability of it surviving for another 5 plus 1 year, given that it has already survived for 5 years. So here our knowledge of conditional probability, remember this is from the conditional probability, will come in handy to find this out. So we need to find this out, and let's do some maths to get this done quick. So do you remember what is the conditional probability? P of A given B is equal to P of A and B by probability of B is the formula. So what do we need to find? So this is your time, say for example this is your time t, this is your t plus s, okay, and we know that it has survived for some time x greater than t, okay, it has survived for, this is the region for x greater than t, and we want to find out what will be the probability of this thing surviving for this period. This is say t greater than s region, sorry, x greater than t plus s, this is your t, and this whole part is say s. So we want to find this survived till this time, and I'm here. So it has survived for 5 years. I'm here. It has survived for greater than 5 years, and now I want to find whether it will survive for one more year, and whether this survival is dependent on the time it has, that whatever time it has already survived. That is the whole thing we need to find, that whether it holds memory or it doesn't hold memory. So what will be A intersection B? What is the common area between x greater than t and x greater than t plus s? This is a common area, right? It is, this part is common to both x greater than t and x greater than t plus s. This is the common area. So we can we say that this is equal to that px greater than t plus s, given x is greater than t, is equal to this A intersection B area. Can we write it as probability of x just greater than t plus s, given, and what is b? B is x greater than t. This is our intersection part, this common area. So what was the formula? This was e to the power minus lambda x here of anything, probability of, from the CDF we know that, right? Probability of from the exponential distribution, x greater than x is equal to e to the power minus lambda x. So now let's substitute this. This will be e to the power minus t plus s by e to the power minus, sorry, lambda times minus lambda. This x will be replaced by this, and this will be minus lambda t. Lambda will be there. So do this. So I'll do lambda t minus lambda s, and this will come up in the, from the denominator, this will become lambda t. So this and this will cancel off. What will be the final value? This is equal to e to the power minus lambda s. Do you see this doesn't have any t term? The t term is not there, and that's what is the proof that exponential distribution is memoryless. You see here, it doesn't have any t in this term, final term. Okay, so we can write that the conditional probability, whatever you have computed, conditional probability does not depend on time t that has already passed or survived. Okay, so that's why this implies exponential distribution is memoryless. Hence proved. Okay, I hope this is clear.